Today we'll be talking about the extreme value theorem. So to begin this discussion, we first have to look at a definition of something called a critical number. So let's go ahead and look at this definition that I've written out here. So first of all, it says let f of x be defined at x equals c. Then if f prime of c is equal to 0, or if f of x is not differentiable at x equals c, then c is what we call a critical number. Okay, so the two different situations we're looking at here. The first one is saying that f prime of c is equal to 0. So that would be something like a situation like this, maybe, where we have this point at the top that's a relative maximum. So remember, in that type of situation, we would have a horizontal tangent line at that point, which would mean that our derivative is equal to 0. Okay. Now the other situation, it said f of x is not differentiable at c. So that would be the type of situation where we had some sort of sharp turn in our graph at c. So remember, any type of sharp turn, your function is not differentiable. So in this case, we would say f prime of c does not exist. Okay, so if the derivative is undefined, but the original function is defined, then that's also going to be a critical number. Okay, so essentially what we're looking at here is these critical numbers are points where our function has a relative maximum or minimum value. Okay, so if the function has a relative max or min, then we'll have a critical number at that point. Okay, so let's go ahead and let's look at a couple examples of finding critical numbers. All right, so let's find the critical numbers. For each function. All right, let's start with f of x is equal to 2x cubed plus 6x squared. Okay, so this is our function. In order to find our critical numbers, we need to start by taking a derivative. And this is just going to be straightforward power rule. So bring down our 3. If we multiply to the 2 that's already there, we get a 6. And then subtract 1, so it would become a square. And then bring down our 2, and multiply by the 6 that's already there would give us a 12. And then subtracting 1 would just give us an exponent of 1. All right, now one thing I'm going to recommend doing whenever we're finding critical numbers is make sure you simplify and factor your derivative as much as possible. So in this case, we can pull out a GCF of 6x, which would leave us an x plus 2. All right, so then thinking about setting that derivative equal to 0, we would get our critical numbers from our two factors. So from the 6x, we get x equals 0. And then from the x plus 2, we get x equals negative 2. So those would be our two critical numbers for this function. All right, let's go ahead and take a look at another example. Let's say on this one we have f of x is equal to x squared all over the quantity x plus 1. All right, so again, to find our critical numbers, we need to start by taking a derivative. And in this case, to find our derivative, we'll have to use our quotient rule. So remember quotient rule, we look at the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. All right, now again, we want to simplify. So if we distribute our 2x in, we get 2x squared plus 2x, and then minus x squared on the end, all over x plus 1 quantity squared. And then combine like terms, so x squared plus 2x, all over x plus 1 quantity squared. And then if we just factor out a GCF in the numerator, we'd have x times the quantity x plus 2, and still all over x plus 1 quantity squared. Okay, so now that we have our derivative function, we're going to think about finding our critical numbers. So remember back up here for our definition, I told you that there's two ways to have a critical number, either if our derivative is equal to 0 or if our derivative is undefined. Now remember, we have to be careful about the undefined case though, because this is only going to be a critical number if the original function is defined at that point. So if we take a look at our function here, let's start with the 0 case. Let's go ahead and set our function equal to 0. Okay. Well, remember, anytime you're setting a fraction equal to 0, really it just means you're setting the numerator equal to 0. Okay, so our numerator is going to equal 0, and hence we're going to have critical numbers at x equals 0 and x equals -2. Okay. All right, now the other thing we have to think about is anywhere that this derivative function is undefined. Well, if we look at our function right here, because we have a fraction, we can see with the x plus 1 in the denominator that this is undefined at a -1. But looking back up at the original function, it also has that same x plus 1 in the denominator, so it's also undefined at -1. So based on the definition above, the -1 is not a critical number because the original function isn't defined there. So our only two critical numbers are 0 and -2 from where our function is equal to 0. Okay. All right, there's one more example to finding critical numbers in the notes that I posted on Blackboard, but I'm going to go ahead and start talking about the extreme value theorem. Okay. All right, so here is our extreme value theorem. So it says if f of x is continuous on a closed interval a to b, okay, so that's a condition we have to satisfy first, then f of x has both a maximum and a minimum value on that interval a to b. Okay, so to kind of illustrate this, I've gone ahead and drawn two graphs here. So our first one, we have this interval a to b, and we can see that this is a continuous function on this interval. So if we think about our minimums and maximums on this interval, well, we can see that right here, we have a turning point. Okay, it's a peak up there. So this would be a relative maximum, but it's also the highest point on the entire graph. So it's also an absolute maximum. So it functions as both in this case. Well, down here we have this point that's a little valley in the graph, which means it's a relative minimum. But again, seeing as how it's also the lowest point on the entire graph, it's also an absolute minimum. Okay, so up here when I say that f of x has both a maximum as well as a minimum value, I'm referring to the absolute max and the absolute minimum. Okay. All right, so we can see from this example that it's possible that our absolute maximum and minimum can occur at those turning points. Well, from what we looked at above, we know that those turning points, those relative maximum and minimum points, occur where the derivative of the function is equal to 0 or where the derivative is undefined. Okay. All right. Now the other thing that can happen here, if we look at this next example, we can see again we have this peak right here. Okay, so that would be, again, a relative maximum because it's a turning point. But then also, since it's the highest point on the entire graph, it's again also an absolute maximum. Okay. Now in this instance, though, if we look for our absolute minimum value, it actually occurs right over here at our endpoint A. This would be our absolute minimum. So not only can our max and min values occur at the turning points, but they can also occur at the end points, okay? So with this extreme value theorem, it's telling us that somewhere within this interval, we will have a maximum and a minimum value. There will be a low point and there will be a high point. Those can either occur at the relative max and mins, which is where our derivative is equal to 0, or they can occur at the endpoints. All right, so let's go ahead and let's take a look at an example of using this extreme value theorem. So we're going to find the extrema on the closed interval. All right, let's start with f of x is equal to 3x to the 4th minus 4x cubed on the interval -1 to 2. All right, so we're trying to find the minimum value and the maximum value on this closed interval, okay? And from what I was saying above, that means we want to check the endpoints because a maximum or a minimum could occur at one of the endpoints, but we also want to find all of our relative maximum and minimum points, which is essentially finding our critical numbers. All right, so let's start with those critical numbers, which means we need to find a derivative. So this is just simple power rule. So we get 12x cubed minus 12x squared. We can factor out a GCF of 12x squared, which would leave us with an x minus 1. All right, so then to find our critical numbers, set the derivative equal to 0. And that's going to put our critical numbers at 0 and 1. Okay, so we know that our maximum and minimum values could potentially occur at these critical numbers. They could also occur at the endpoints. So now we're going to test all 4 of these values back in the original function to see where we have a low point and where we have a high point. So I'm just going to organize this in a little table. Here we're looking at our original f of x function. Okay, so first our left endpoint was -1. Then we have our 2 critical numbers, 0 and 1, followed by our right endpoint of 2. Okay, so we're looking at left endpoint, critical numbers, right endpoint. All right, so now we're just going to plug all 4 of these values back into the original function. Okay, so when we plug those in, f of -1 would give us 7, f of 0 would give us 0, f of 1 is -1, and f of 2 is 16. Okay, so now we're looking for the maximum and the minimum. So in order to do this, we're really just looking for what's the lowest number, what's the highest number. So we can see by looking at this, -1 is the smallest number here. So this would be our minimum. that would be at the point 1, -1. And then 16 is our biggest number, so that's our maximum. And that's at the point 2, 16. Okay, so by the extreme value theorem, we know that we have a max and a min somewhere on this interval. So we found our critical numbers, and then we checked both endpoints along with those critical numbers back in the original function and picked out our minimum and our maximum values. All right, let's take a look at one more example with this extreme value theorem. Let's try f of x is equal to 2 minus, let me actually do f of x equals 2x minus 3x to the power of 2/3. And let's look at the interval -1 to 3. All right, so just like the last one, we're going to start by finding our derivative, which will help us find our critical numbers. So our derivative in this case, if we use our power rule, we would have 2 minus, and then here we'd bring down our 2/3 and subtract 1 from our exponent. So simplifying this, we would get 2 minus 2 divided by x to the power of 1/3. Okay, so that's our derivative. Now, if we want to, we could also go ahead and put this all over a greatest common denominator. That's kind of up to you exactly how you want to work with it. I'll go ahead and do that just to, or no, I'm sorry, not greatest common denominator, least common denominator. I misspoke there. Put this all over a least common denominator. So if we think about this as being over 1, then that would give us 2x to the power of 1/3 minus 2 all over x to the power of 1/3, putting that all over a least common denominator. Okay, so then we want to think about our critical numbers. So remember, for that, we want to think about both where our function is equal to 0, as well as where our function is not differentiable. So if we go ahead and set this equal to 0, remember that's really just the same as setting the numerator equal to 0. So I'm going to go ahead and pull out a 2 from this. All right, so that would be a critical number then at x equals 1. Now the other thing we need to think about, though, is where our derivative function is undefined, which in this case, looking at our denominator here, we can see that this is undefined at x equals 0. And looking back up at the original function, this doesn't have any domain restrictions, which means x equals 0 is also a critical number. Okay, so we have 2 critical numbers. Now we want to check both critical numbers along with both of the endpoints back in the original function to see which one's a max and which one's a min. I'm going to make a little table again. Checking these back in the original function. All right, so we have our left endpoint at -1. Then we have our critical numbers at 0 and 1. And then we had our right endpoint at 3. Okay, so I'm just going to plug all these numbers back into my original function. And I got f of -1 gives me a -5. F of 0 gives me 0. F of 1 is -1. And f of 3 is -0.24. Okay. All right, so then based off of this, we can pick our minimum value and our maximum value. So the biggest number in this case is 0. That puts our maximum at the point 0, 0. And our minimum value, our lowest number, is the -5, which puts our minimum at the point -1, -5. All right. So if you want to see one more example, I have it listed out in the in the notes that I posted on Blackboard, but otherwise that's where we'll end our video for today.